This lesson is on limits at infinity. So we have this first graph here. When we're looking at infinity, for example, this graph, if we want to think about what is happening to this graph as the x values go towards positive infinity, you can see that we have this leveling off right here. So the limit of this function f of x as x goes to infinity is trying to get to -3, and it will never really technically touch it, but it'll level off at that. But we could also look at the limit as x gets really large in the negative infinity direction, and so you can see that it also is trying to level off at -3. All right, so that's our first example, and just notice here that this function is crossing over this horizontal asymptote because it's not saying that it equals -3 for small values of x. The limit is going to approach -3 for large negative and positive values. Okay, so limits at infinity and horizontal asymptotes. If f of x becomes arbitrarily close to a finite number L for all sufficiently large and positive x, then the limit of f of x as x approaches infinity is equal to L. And so that tells you that there is a horizontal asymptote at y equals L. If f of x becomes close to a finite number m sufficiently large and negative x, then the limit of f of x as x approaches negative infinity is equal to m, and therefore we would have another horizontal asymptote. So we get here that you could have two horizontal asymptotes. If you go to the right and there's one, and you go to the left and there's another, you could have one like this one, or you could have 0 horizontal asymptotes. Okay, so example 1, here we've got this function. It's a continuous function. It seems to be leveling off here. So we would say the limit of f of x as x approaches negative infinity is 2, and the limit as x of f of x as x approaches positive infinity is 2, and you can see that tells us there is one horizontal asymptote at y equals 2. Okay, so let's look at this example 2 here. We have this function. It's a very common rational function, a basic rational function, f of x equals 1 over x. So remember, this is a continuous function by definition because 0 is not in the domain. So this is continuous through the life of its domain. The limit of 1 over x as x approaches negative infinity is going to 0, and the limit of 1 over x as x approaches positive infinity is also equal to 0. All right, so again, you now have a horizontal asymptote at y equals 0. But you also have a vertical asymptote. Remember, vertical asymptotes come from where the denominator can't equal 0 and it doesn't cancel. So there's a vertical asymptote at x equals 0. And I'm mentioning this because there's a specific question in WebAssign that it was really kind of a trick question. So we'll tell you this. It is true that a continuous function, remember definition of continuous function, it's continuous on its domain, right? So if you have a continuous function, it will never cross or intersect the vertical asymptote. Right? However, a discontinuous function could cross the vertical asymptote. So it is possible. So what would a discontinuous function that would look like that would do that? Well, we can create one. So we could say, all right, let's create this function here that looks like 1 over x whenever x does not equal 0, but is 0 when x equals 0. And now that would become a discontinuous function because it's all real numbers in the domain, and it would look like this. And now it would actually cross that vertical asymptote. And so I had to think about that situation because of the first question, I think, in this WebAssign. It asks a trick question. Okay, so let's continue. So limits at infinity of powers and polynomials. Okay, so if we are just looking at polynomials for a second, we know polynomials are continuous functions. And if we have the limit of x to the n, and n is even, so if you have an even degree polynomial, if you go way back to 171, remember if the degree is even, the n behavior is either going to be up, up, or down, down, depending on this understood coefficient. So when you have an even degreed polynomial, as you go to positive infinity, it's going to go to positive infinity. As you go to negative infinity, it's going to go to positive infinity. So like this, the limit as x approaches x to the 4th, it looks like this. So x to the 4th looks like this. It looks like a u, but sort of flatter. Its end behavior as x goes to infinity, it goes to positive infinity. As x goes to negative infinity, it goes to positive infinity. So you can tell a lot by just looking at the degree. Okay, so if you have as x, if you have x to the n here and n is odd, then I'll just go ahead and give you the example I'm thinking of. Remember x cubed? That's an odd degree. Remember that end behavior? That's down, up in behavior. So if you have an odd degree, polynomial, then we know the end behavior, as long as that coefficient in front there is positive, is going to be down, up. So as x goes to infinity, this odd degree polynomial is going to go up or go to infinity, and as x goes to negative infinity, this odd degree polynomial is going to go down or negative infinity. So what we have here is this little property here that I like to use. As x approaches negative infinity of f of x, if this is an odd degree function, then the limit as x approaches negative infinity is equal to the negative or the opposite of the limit as x approaches infinity, if this is odd. See, this and this, positive infinity, positive infinity, negative infinity. So this equals this if we just change that sign to a positive infinity and that to a positive infinity. So we'll look at an example of when we can use that. All right, this property here is helpful when you're going to positive and negative infinity and you have a polynomial in the denominator. It doesn't matter whether that's odd or even. That's going to go to 0. So 1 over positive infinity would go to 0. 1 over negative infinity is going to go to 0. And then D, let p of x be a polynomial. All right, the limit of this polynomial is, all you have to do is just look at the leading term. So that's a flashback from to 171. All right, and then the last thing I'm going to tell you is when you're evaluating these limits, sometimes you get into these situations here. So if you ever get infinity minus infinity, that does not equal 0. That's indeterminate. In other words, you have to keep looking for another solution. But if you get infinity plus infinity, that's going to equal infinity. Same thing if you get infinity divided by infinity, that's not equal to 1, because infinity really isn't a number. It's more of an idea. This might be bigger than that, infinity. So that's also indeterminate. It's an indeterminate form. But if you get infinity times infinity, that would be infinity. So keep in mind that you can't stop with infinity minus infinity or infinity divided by infinity. Those are indeterminate forms. Okay, so now we get to our examples of taking limits. This would be the second part of that practice worksheet that I gave you. We can practice infinity. So we're going to use the previous theorems that we just talked about, along with algebraic manipulation, to evaluate these limits. Now, when we're doing limits at infinity, limits to infinity, the general rule, there's going to be an exception, is what you're going to do to show your work is you're going to divide each term in the numerator and the denominator by x raised to the highest power in the denominator. Okay, so what this is saying is if you want to find the limit as x approaches infinity, and you want to show your work, what you're going to do is you're going to look at this denominator, and the highest power in the denominator is x to the 1. So I'm going to show all my work here so you can see that it's algebraically accurate to do this. It's okay to do this. I'm going to divide the numerator by x to the 1. Okay, that's the same thing as multiplying by the reciprocal, which is 1 over x. So I'm going to multiply both the top and the bottom by 1 over x. Okay, and that means I'm going to distribute over this subtraction here. Okay, so that's going to be the limit as x approaches infinity of 5 times 1 over x is 5 over x minus 2x times 1 over x is 2x over x over, distribute that 1 over x to both of these, and you get x divided by x. So x times 1 over x is x over x minus 4 times 1 over x is 4 over x. So this is why it works, because I'm multiplying by a convenient form of 1. That's legal, and I'm distributing. That's legal. So now you can do the shortcut. You can take the highest term of the denominator and divide each term in the numerator by that. Okay, so then we're going to simplify. And so 5 over x is 5 over x, and minus 2x over x is minus 2, and then x divided by x, that's 1, minus 4 over x. Okay, and now we're going to apply this rule right here, rule C. If we can get a constant over some power, it's going to equal 0. Okay, so when you get the limit as x approaches infinity of 5 over x, that's 5 over infinity. That's going to go to 0. And that's the notation you can use. All right, minus 4 over x, when you get there, you put infinity in there, 4 over infinity, that's going to go to 0. So you get the limit as x approaches infinity of negative 2 over 1, which is negative 2. Okay, so that's how you show the work there. You can pause the video and try this one, B here, and come back with me. Did you divide each term by the highest power of the denominator? Then that's going to give you 4 over x cubed minus 2 over x minus x cubed. Well, I didn't do that right. Divide by x cubed minus 6. These cancel. And then over 2x cubed over x cubed is 2. plus 1 over x cubed. Then apply the limit rule. We're going to infinity, so that has constant over x cubed, that goes to 0, minus 2 over x, that goes to 0, 1 over x cubed, that goes to 0. So the limit as x approaches infinity of negative 6 over 2 is equal to negative 3. Okay, so let's go into the next two, and let's look at them together for a second. All right, let's see how they're the same. They both have a square root, but this numerator is just the square root, and this is a square root minus another term. So just keep in mind that the way you're going to do these are different. All right, we're going to do the same thing here, but this square root is going to cause us to have to think a little bit. So the highest power in the denominator is x cubed. All right, but when you're under a radical, so we need to go over radicals here. All right, if this is outside the radicals x cubed, what would go under the radical so that the square root of it would equal x cubed? And so with exponents, you really just use multiplication because there's a 2 there. So the square root of x to the 6th, 6 divided by 2 is 3. Right? So that relationship is going to be needed here. So I'm going to show on my work, because if I don't, you might be like, where did she get x to the 6th? But it's right here. So what I'm going to do is I'm going to show my work. So I'm going to multiply by convenient form of 1, and I'm going to multiply by the square root of 1 over the square root of x to the 6th over the square root of 1 is 1, and the square root of x is 6 is x cubed. So that's a convenient form of 1. Okay, so if I just distribute that, that's going to give me 9x to the 6th over x to the 6th minus x over x to the 6th, because it's under the radical, over x cubed over x cubed plus 1 over x cubed. So it looks like I'm doing something different in the top than I am the bottom, but I'm really not, because the square root of x to the 6th is x cubed. So that's how you handle the radical. All right, so then that would give me the limit as x approaches infinity of the square root of 9 minus 1 over x to the 5th. X to the 1 divided by x to the 5th is 1 over x to the 5th over 1 plus 1 over x cubed. So then we'll apply this infinity to this denominator. That's going to go to 0. 1 over x cubed at 1 over infinity, that's going to go to 0. So that's the limit as x approaches infinity of the square root of 9 over 1, which is 3. Okay, so the next one is like Webassign number 10, and you might recall we learned this trick when we were doing the other types of limits. What do you do if you have the square root minus x? Well, you can't just apply the infinity. If you put the infinity in there, you would get infinity plus 1, which you'd end up with infinity minus infinity, which we said is indeterminate. So we have to come up with a trick, and that trick for this type, I didn't need to do it over here. I do need to do it over here, is to multiply by the conjugate, but you have to multiply the top by it and the denominator by it. So the conjugate of square root of x squared plus 1 minus x is the square root of x plus 1 minus plus x over itself. Okay, so I'm going to multiply all of that. So that's going to give me the limit as x approaches infinity of, so this needs to be FOILed out. Okay, and so I know what happens with conjugates. First of all, the square root times the square root is just going to, the square roots cancel, and you're just left with x plus 1. I don't really need to do the outer or the inner because they cancel. That's what conjugates do. But then I have minus x times positive x, which is minus x squared, over the square root of x squared plus 1 plus x. So x squared minus x squared, they cancel. And so now you have the limit as x approaches infinity of 1 over the square root of x squared plus 1 plus x. So now you have to remember, just like we did over here, all the other ones, the denominator's largest power isn't x squared. It's the square root of x squared, which is x. So I'm going to divide the top by x. Okay, so show my work, 1 over x divided by 1 over square root of x squared. That's 1. So I'm going to get 1 over x over square root of x squared plus x squared over x squared plus 1 over x squared plus x over square root of x squared, which is really just x. And that's going to give me, that's going to go to 0. Let's just finish this out. That's going to go to 0. So just in case this doesn't happen, I'm going to keep going because I already know it's 0. But that's 0 over, that would be 1 square root of, that go too far, square root of 1 plus 0, square root of 1 plus 1. So you would get 0 over 2, which is 0. Okay, so this next one's kind of an important one. I believe it's like web assign number 12. But what's happening here is you have x is going to negative infinity. And so when something is going to negative infinity, it tends to cause some problems because it goes in opposite, directions as the infinity one if you have an odd degree, right? If it's an even degree, it's going to be up, regardless. But if it's an odd degree, if you go to negative infinity, it will go down. If you go to positive infinity, it's going to go up. So basically, you have to think about the degree. All right, and it's only the odd degrees that really give you trouble. Okay, so what I do when I think about something like this is, we could split it all up and do all that, but you just want to look at the numerator and notice that this square root is always going to be a positive number. So it's not going to affect the direction, the end behavior. What's really the driving force of this is this odd degree function right here. So whenever I have a limit as x approaches negative infinity with an odd degree, I love to use this right here. So this b, okay, if you have an odd degree, the limit of f of x as x approaches to negative infinity is equal to the negative of the limit of f of x as x approaches positive infinity. So I like to use that one a lot. So this one's kind of tricky because not only is it odd, there's a square root on top, but the square root it's a principal root. So no matter what, if I went to negative infinity forever and ever, this is positive. It's not ever going to be negative. So I really just have to worry about that. So what I'm going to do is I'm going to say, well, this limit is the same as the opposite or negative of the limit as x approaches infinity of the square root of 9x to the 6 minus x over x cubed plus 1. I'm just going to need to remember that negative there. And so then it's an infinity limit, so we're going to divide by the highest power of the denominator. But you also have a square root, so we have to remember that the square root of x to the 6 is equal to x to the third. So I get to divide this by x to the top by x to the 6th because it's under a radical. So that would be the net opposite of the limit as x approaches infinity of 9x to the 6 over x to the 6 minus x over x to the 6. All of that is under the radical. That's why I'm dividing by x to the 6th. And then down here, I'm going to divide by each term by x cubed. So I didn't show as much work there. I didn't multiply by the convenient form of 1 because it's just going to mean I'm dividing everything by the same thing. All right, so then this gives me the opposite of the limit as x approaches infinity of the square root of 9 minus 1 over x to the 5th over 1 plus 1 over x cubed. Then we can apply this rule here. When you put infinity in that, that's going to go to 0 because you have x in the bottom over a constant. Here, that's going to go to 0. So you're going to get negative limit as x approaches infinity of the square root of 9 over 1, which is negative 3. So if we didn't do this little trick here, we would end up thinking the answer is 3. But it's not 3. It's negative 3. So you have to look for that odd degree so you can apply that rule that we just used. Okay, so this next part is really review from 171. If you want to find the horizontal asymptote and use some shortcuts, it's all about the degree. So if you have degree same over same, the same degree on the top as the bottom, then the horizontal asymptote is just going to be y equals k over h. These are for polynomials. If you have degree small over large, then kind of what we've just been doing, the denominator is going to get big as you go to infinity, at a much faster rate than the numerator. So it's going to, the horizontal asymptote is going to be y equals 0. If you have degree large over small, there isn't a horizontal asymptote because the numerator is going to keep getting bigger and bigger and bigger. But you might have something called a slant asymptote, and you would use long division to find it, since the limit of f of x would just go to infinity. All right, now remember that vertical asymptotes occur where the reduced function denominator zeros equals 0. So the factors that don't cancel are where you get your vertical asymptote. So let's look at this example. It says use limits to determine the horizontal and vertical asymptotes of h of x equals x squared minus 4x plus 3 over x squared minus 1. So we might as well factor so that we can reduce if we can. And so the numerator factors into x minus 3, x minus 1, and the denominator factors into x plus 1, x minus 1. So they cancel, and so remember those factors, that x equals 1, that would give me a whole. But this factor that doesn't cancel, x plus 1 cannot equal 0, x cannot equal negative 1. So there's a vertical asymptote at x equal negative 1. We'll finish this out. X minus 1 can't equal 0 as well, but since that factor cancels out, there is a whole at x equal 1. Okay, so we have a vertical asymptote at x equal 1. Now what that means in terms of limits is that the limit as x approaches negative 1 of this function if we go check it from the left, that's going to give me a constant negative 4. Go ahead and put that in. And then a small number close to negative 1 to the left would be like negative 0.101, which would be a small negative, which would lead to positive infinity. And the limit as x approaches negative 1 from the right would be the limit as x approaches negative 1 from the right of some constant, the negative 4. We can just put negative 1 here. And then the number to the right of negative 1 is slightly smaller than 1, so that would be a small positive. So that would go to negative infinity. So you can see that's what the limits are going to look like when you have a vertical asymptote. All right, the horizontal asymptote, these are two polynomials, so they just have to do with the degree. So this is a degree 2 in the top, that's a degree 2 in the bottom. So we can see that there is a horizontal asymptote at y equal 1 from using 171 property. But what that would look like is the limit as x approaches infinity of x minus 3 over x plus 1. We can just use the reduced function. If we divide everything by x, you get x over x minus 3 over x, and x over x minus 1 over x. They go to 0, and you get the limit as x approaches infinity, you get 1 over 1, which is 1. Okay, so then how would you think through the limit as x approaches negative infinity of this one? Well, we just talked about this odd degree property. So this is an odd degree. So you could apply the limit rule and make this negative limit as x approaches positive infinity of this. But this one is also an odd degree polynomial. So it would be the negative of the limit as x approaches infinity. So this one, the negative over the negative is just going to cancel. So this would mean that the limit as x approaches positive infinity is going to be the same as the limit as x approaches negative infinity, which we just found. So that's the limit connection to horizontal and vertical asymptotes. Okay, so take a look at these examples. Sometimes you don't use the rules that we were just using. Sometimes you can just sort of use an intuition, a logical analysis. So, for example, this one says the limit of cosine of x as x approaches negative infinity. Now, this is not a polynomial, so this odd to even degree thing isn't what we're going to need to know, but you should know that cosine is a function that, as we go to infinity, it's just going to keep going up and down, and when it doesn't have a number in front, it's just going to go up to 1 and then down to negative 1, right? So we just know that as x goes to negative infinity, cosine of x is going to go up to 1 and down to negative 1, up to 1 and down to negative 1. So it's just never going to level off or go anywhere. So that limit just doesn't exist. And then this one, the limit of 10 plus e to the negative x as x approaches infinity, you can just rewrite this. So if ever you have a negative exponent, put it in the denominator, because we have that wonderful rule that if we can get a constant in the numerator and something that's growing in the denominator and we're going to infinity, that's just going to go to 0. So this limit is just 10. Okay, so those are just two very specific examples of, well, we did use a little rule here. So we want to remember that if you have a negative exponent, try to get something in the denominator so that you can make it go to 0 as x approaches infinity. And then this is a very specific case. This is called the squeeze theorem. And it sounds really hard, but it's really very manipulative. If you have the right conditions, you can use the squeeze theorem. And so we can create this condition. All right, so if you've got three functions and the middle function is bigger than the first function but smaller than the last function, and then you can find that these two limits at the beginning and the end are both the same number, then it stands to reason that this function will have that same limit. And so the picture is a little weird to see, but what we're doing is just going through this example here. This is the function x squared times sine of 1 over x, and this is what it looks like. All right, and we want to find the limit of this function as x approaches 0. So change that a to a 0. It should say a 0 right there. And you can see that from the left and the right, it's equal to 0. So this is just an exercise in an example of how to build the situation. What you want to try to do is take this function, this x squared times sine of 1 over x, and make it the middle function, and then do some bounds by it. So what we're going to do, a lot of times this is what's going to happen. You see how it's x squared times that sine of x? Well, let's consider sine of 1 over x, excuse me. All right, well, we just talked about up here that no matter what I put in to a sine function's argument, just like the coefficient, it's going to cycle through. It's going to get as high as 1. It's going to get as low as -1. So by doing that, we just built this situation. All right, now we can bring this x squared in, and since x squared is positive, no matter what we put in for x, we can multiply it to all three without affecting these inequalities, because if you multiply a positive number, you don't have to worry about switching the sign. So I'm going to multiply this by x squared and get -1x squared. Multiply this middle one by x squared and get the function that we were thinking about. And then I'm going to multiply 1 by x squared. Okay, and so now I can take the limit as x approaches 0 of -1x squared, and then the limit as x approaches 0 of x squared times sine of 1 over x, and then the limit as x approaches 0 of x squared. All right, and we can just direct substitute 0 in there, and you're going to get 0. We don't know this one, because if we would put, you can't put 0 in here because you get undefined right there. But we can direct substitute 0 into this one, and you get 0. Therefore, by the squeeze theorem, we now know that the limit as x approaches 0 of x squared times sine of 1 over x is also equal to 0. And so this is the picture. This is x squared, and this is -x squared. And it seems really hard because, how did I know to do all this? Well, most of the time when I've seen the squeeze theorem, it's been something like that. It involves a sine or cosine function that has a natural boundary to it. So you get that, and then you just can figure out, if I multiply by x squared, then I'll get my original function.